This video looks at the case of three planes intersecting in a line. So the example here says we have three simultaneous equations and they have infinitely many solutions. Okay, so if they have infinitely many solutions, we know they're coincident, they're the same plane, or the planes intersect in a single line. So my first step would be just look at the equations and see if they're multiples of each other. And you can see that's not the case. So, for example, there's no common multiple of the three equations. So we know we're going to be looking at the planes intersecting at a single line. So just have a little idea of what you're looking at before you start. So we need to solve the three simultaneous equations. We're going to use Gaussian elimination. So you can do that on your own. Pause the video, have a go, watch it to see if you're correct. So our starting point is to put those equations in matrix form. Now we need to solve. Now I'm going to do something I haven't done before. I'm going to do two steps in one. So I have two negative ones here and I have a 1 there. So I'm going to go row 2 plus row 1 and I'm going to go row 3 plus row 1 at the same time. So negative 1 plus 1 is 0, negative 3 plus 2 is negative 1, 2 plus 3 is 5, 2 plus 13 is 15. Negative 1 plus 1 is 0, negative 4 plus 2 is negative 2, 7 plus 3 is 10, 17 plus 13 is 30. Now I'm going to look at this negative 2 and make it a 0. And I'm going to do that by working with my row 2. So I'm going to go row 3 minus 2 lots of row 2. So 0, negative 2 take 2 times negative 1 is negative 2 plus 2 is 0. 10 take 2 lots of 5 is 10 take 10, which is 0. 30 minus 2 lots of 15 is 30 minus 30 is 0. Now this is interesting. We have a line of zeros. That's case 3, infinitely many solutions. Okay, 0 always equals 0. That's fine. It'll always be the case at infinitely many solutions. Now we're going to keep going just a little bit to make our lives a little bit easier. So first of all, I'm going to look at that negative 1 and make it 1. So I'm going to go row 2 times by negative 1. So I have 0, 1, negative 5, negative 15. And I'm going to look at row 2 to make that 0. So what I'm trying to do is just have two variables in each row. So for this one, I'm going to go row 1 minus 2 lots of row 2. So 1 minus 2 lots of 0 is 1. 2 minus 2 lots of 1 is 0. 3 minus 2 lots of negative 5 is 3 plus 10, which is 13. 13 minus 2 lots of negative 15 is 13 plus 30 is 43. So from here you can see that I've got zeros in every row. So two variables in each row. The last one is my 0 equals 0, which I already worked out. The row 2 is at y minus 5z equals negative 15. And row 1 is that x plus 13z equals 43. So now let's answer our questions. Part A said, describe these solutions with the use of a parameter. So just like we did when we had two variables, we're going to let z equal lambda. And you'll see why I went a little bit further with my reducing. So my first equation, x plus 13z equals 43, I can replace the z with lambda. So x plus 13 lambda equals 43. So x equals 43 minus 13 lambda. My other equation was y minus 5z equals negative 15. So y minus 5 lambda equals negative 15. Y equals negative 15 plus 5 lambda. So therefore, we have x equals 43 minus 13 lambda, y equals negative 15 plus 5 lambda, and we have z equals lambda. Part B, give a geometric interpretation of the solution. The equations represent three planes that intersect along the line given by the parametric equations x equals 43 minus 13 lambda, y equals negative 15 plus 5 lambda, and z equals lambda. Now, if you're struggling to understand that, go back and watch those introductory videos. The reason why we did two variables where we introduced our parametric equations and our lambda, those intro videos should have helped, and also the intro videos to the three-dimensional plane should have helped.